Hello friends, welcome to the session. Myself Soumya, Assistant Professor, Department of Mathematics, Government First Grade College, Tiptur. So, in this session we shall see the concept of limit points. So, we are dealing with the concept of limit points, like definition and the theorems on limit point. So, the definition, what is the definition of limit point of a set? So, a point P in the set of all real numbers R is said to be a limit point of the subset S of R. So, we consider a point P in the set of real numbers R, and it is said to be the limit point of the subset S of R if every neighborhood of P contains infinitely many points of S. So, we consider a point P in R and we take a subset S of R, then P is said to be the limit point of the subset of S if every neighborhood of P contains infinitely many points of S. So, this is the definition of limit point of a set. So, now we shall see the theorem. A point P is a limit point of the set S. A point P is a limit point of the set S if and only if every neighborhood of P contains infinitely many points of S. So, a point P is said to be the limit point of S if and only if every neighborhood of point P contains infinitely many points of S. So, we shall see the proof now. The if and only if is there, so we have to prove the necessary part also. So, the necessary part is that let P be the limit point of S. So, we consider P as the limit point of S. Now, we have to show that every neighborhood of P contains infinitely many points of S. So, we have to show that every neighborhood of P contains infinitely many points of S. Let, if possible, every neighborhood of P contains a finite number of points. So, we go by the method of contradiction. So, every neighborhood of P, point P contains a finite, instead of infinite numbers, we take a finite number of points P1, P2, P3, P4, etc., Pn, different from P, which are all different from the point P. Again, let epsilon be the minimum of the modulus of P1 minus P minus P1, comma, modulus of P minus P2, modulus of P minus P3, etc., modulus of P minus Pn, so which is greater than 0. So, we take a number, small number epsilon, which is the minimum of the difference of P minus P1, P minus P2, P minus P3, etc., P minus Pn, and it is always greater than 0. So, then P minus epsilon, comma, P plus epsilon is the neighborhood of P which contains no point of S. So, by the above statement we can say this real number P minus epsilon, P plus epsilon is there, is a neighborhood of P and it contains no point of P. So, P is not the neighborhood of S. But by the definition of the limit point, so we say that every point P has infinitely many neighborhood points in the set S. So, this becomes the contradiction. Therefore, our assumption that every neighborhood of P contains only finite number of points of S is wrong. So, we can see that every point of P contains infinitely many neighborhood in the set S. Hence, we say every neighborhood of P contains infinitely many points of S. The condition is sufficient. Suppose every neighborhood of P contains infinitely many points of S, then obviously every neighborhood of P and hence P is a limit point of S. And now the next theorem, prove that a real number x is a limit point of the set S if for each n belongs to the set of natural numbers, the open interval x minus 1 by n, comma, x plus 1 by n contains a point of S other than x. So, the theorem statement states that prove that a real number x is a limit point of a set S if for each n belongs to the set of natural number n, the open interval x minus 1 by n, x plus 1 by n contains a point of S other than x. So, the proof, the necessary part, let x be a limit point of S, let x be a limit point of S, then for every epsilon positive, the open interval x minus epsilon, x plus epsilon intersection S minus a singleton set x is a non-empty set. So, the intersection of the open interval x minus epsilon, x plus epsilon and S minus singleton set x is a non-empty set. Now taking epsilon is equal to 1 by n and 1 by n is greater than 0 for all n belongs to the set of natural numbers, we have the open interval x minus 1 by n, x plus 1 by n intersection S minus a singleton set x is a non-empty set. So conversely, for each n belongs to n, let the open interval x minus 1 by n, x plus 1 by n contains a point of S other than x. Therefore, for every epsilon positive, we can choose a natural number n such that n is greater than 1 by epsilon. That is, 1 by epsilon is less than 1 by n is less than epsilon and minus 1 by n is greater than minus epsilon into x plus 1 by n, which is less than x plus epsilon, and x minus 1 by n is greater than x minus epsilon. So this implies the open interval x minus 1 by n, x plus 1 by n is a subset of x minus epsilon, x plus epsilon. Since the open interval x minus 1 by n, x plus 1 by n contains a point of S other than x, so does the open interval x minus epsilon, x plus epsilon. So does x minus epsilon, x plus epsilon. Now for every epsilon positive, the interval x minus epsilon, x plus epsilon intersection S minus singleton set x is a non-empty set, which we can say that x is a limit point of S. Now the short answer, you can define the limit point of a set, the first one, and the second is give an example of a set whose limit point is not an element of the set, and another example, give an example of a bounded set having limit point. And the descriptive questions for you: prove that a very infinite and bounded subset of R has a limit point. And the second question, the derived set of an infinite bounded subset of R is bounded. And the references: The Real Analysis by N.P. Bali, Principles of Mathematical Analysis by Walter Rodin, Mathematical Analysis by S.C. Malik, and Elements of Real Analysis by S. Narayan and M.D. Rai Singhania. Thank you, friends.